bit about complexity issues and ways to deal with that. So with coalitional games, there is an obvious source of computational complexity lying in that the game is given by the set of agents and the characteristic function that specifies the value of each coalition. That the input of the game is exponential in the number of agents. Okay, and that's not cool. So can we do something about that? And there are different ways to try and represent the game in a more compact way that some of them are not fully expressful, meaning that we cannot represent any coalitional game in this way. But they make sense in a particular domain. Some of them are fully expressive, meaning that in worst case it still would take exponential space to represent the game, but in some domains this representation actually does give a more compact representation. So let's talk about some of them of different sorts and see how that affects the complexity of finding the Shapley value, checking for the membership in the core, checking for the non-emptiness of the core, and all those things. Many coalitional games are, and if we have time at the end, I'll give you some specific examples. Many games are defined on graphs. And graphical representation also can be considered as one general way to represent a game. And there are graph games. Or weighted graph games, which are defined as follows. We have weighted undirected graph. So now this is the set of vertices, and this is the set of weights where Wij actually lies in the set of nodes squared, specifies the weight of edge I, j. That's actually one, that's the number. This belongs to. In fact, the graph is undirected, so we will have a bit less than that, but still that would be polynomial in the number of agents. Well, that's just the graph, and we talk about a cooperative game that is associated with the graph in the following sense. The set of agents would correspond to the set of vertices. So agents are nodes. And for each coalition of agents, which is a subset of nodes now in the graph, the value of the coalition will be given as the sum of weights of all the edges that are inside the subgraph defined by that set of nodes, right? So for all coalitions C, the value of C would be the sum of W j belong to C. Now it's easy to see that, so now the representation is more compact, right? I only need to specify at most this many number of values, and then the rest are computable already. So we don't have to make it part of the input. Also, if the weights are positive, then the game is monotone. That is for a subset of the, if we have S a subset of T, then the value of S is less or equal than the value of T. But that's only for positive, well, non-negative weights. With negative weights, the game doesn't have to be monotone, and that's also easy to see. Add a negative number, so the total value can decrease. Now, this representation is not fully expressive, so there would be games that we cannot represent this way, so this is not a complete representation. An example of a game that cannot be given in this way, the majority game, if you remember, was that? That was the game, a simple game, so that the values of each coalition are either 0 or 1, and each coalition C, whose size was at least the majority, so at least 2, 3 agents, well actually. The majority, say n over 2 alpha value, that would be 1, and 0 otherwise. If you look at 3 agents, for instance, A, B, and C, so what weights would you give to them so that they represent the game in this way, right? A and B together, any pair actually of agents must have the value of 1. So the value of that age must be 1, exactly as that and that one. But then the value of the total coalition will be 3, and we only want 1. Right? So it's not possible to represent this game as a weighted graph. But there are some good things about these games. First of all, in many situations, they actually do make sense. So there are specific examples where this game just reflects some realistic situations. Also, if the weights are non-negative, then checking for the membership in the core becomes an easy problem. So it can be solved in polynomial time. Then we also can easily compute the Shapley value. So for positive weights, it's poly-time check. What do I mean by membership in the core? I'm given an imputation, I have to check if that's the member of the core or not. Also, the Shapley value of each agent I would be given by the sum of half of the sum of weights on all the agents where on all the edges where our agent is present. It's actually very easy to see why that's true. So we remember that the Shapley value is additive, right? So I now can define, I can decompose my game into games G, I, J for each edge. So this would define a game where the set of agents is exactly as before, and it only has one edge with the corresponding weight. Okay. Now in this game, what should be the Shapley value? Right. Shapley value is a symmetric solution, and also it satisfies the dummy axiom. So that means that when I look at any coalition of agents in this graph, only agents I and J that correspond to the edge which is present in the graph would actually contribute something to the coalition where both of them are present. Any other coalition that either I is a member or J, either I or J are not a member, one of them or both, would have value 0, so all the members of those coalitions would have value 0. Coalition where both of them are present, only these two guys actually make contribution, and they make equal contributions, so they are substitutes. So they must have the same payment. Moreover, the other agents who do not contribute anything have to have the payment of 0. Right? So in this game, the value of each agent K, this way, should be 0 for any K which is not I or J, and for I or J, there should be the same number, and that's exactly, so what do they share? The value of the coalition where they both are present is exactly Wij. There's only one edge there. So they share it equally, there would be half Wij. So that's for this particular game. Now, by additivity, our game is actually the sum of those. We have the same set of nodes, and now we put all those edges back there. The Shapley value of each agent would be then, in the total game, right, there would be the sum of their Shapley values in those games defined for each edge, and that would be, so we would only count, they would have positive value only for those edges, for those games where they were present in the edge. So there would be half of it, half of Wkj, J is not K. It's exactly the same. Now for negative weights, let me call them weighted graph games, are not necessarily monotone. And also, it is now hard to test the non-emptiness of the core. And also check if the given second one is actually co-NP hard, meaning that the complement of the decision problem is hard rather than the direct problem. But in general, that means computationally hard. So that's what you need to know. Why this is easy in terms of positive, with positive weights, because then we can use the algorithm for solving maximal flow problem with positive weights, which is easy, and that actually helps to check this one. With negative weights, we don't have that. So those are weighted voting graphs. We will come, not voting, weighted graph games. We will come back to them maybe in the end, or then, if not, then on Thursday. Another representation scheme, which is also, it does not apply to all the games, but it applies to all super additive games. And this is based on the idea that, so in super additive games, what we know, that it always makes sense for the agents to merge because there is some synergy when agents cooperate. The idea is that in practice, not all the coalitions represent those synergies, positive synergies, but in fact they're quite sparse, and that's why we can represent the games by specifying only the values of coalitions where we have such an additional synergy between the agents, and not the values of all the coalitions. And then we may hope for good things. So this is by given the synergy representation. So we have a game and instead of characteristic function, I would write S, given, meaning that that's the synergy representation. So we only specify the values of those coalitions that introduce those synergies, right, which are not additive but strictly super additive. And then the value of all other coalitions we get just by using superadditivity, right? So the value of some coalition C, I look at this coalition and I look at different partitions of that coalition into disjoint sets, and I find the maximal value, the maximal total value that such a partition gives me. Okay. So that's the maximum. We'll do an example right now of all partitions of C and we look at the total value of that partition. So this is the set of partitions. So look, for instance, at this example. We have 3 agents, and the value of each singleton coalition is 1. And for the pairs, we have the value of 1 and 2 is 3, while the values of 1, 2, and 2, 3 is 2, and the value of the total is 4. Now, in the synergy representation for such a game, only specify the values of the singletons and the value of this pair, 1 and 2, because if I add up the values of the members of that coalition, 1 and 2, I will get only 2, but there is some additional value, which is the synergy of the cooperation of these agents. So the value of this coalition I had to specify, while 1, 3, and 2, 3, I could just find by using superadditivity, knowing that the value of 1 and 3, so there is only one partition here into 2 singletons, would give 1 plus 1, that's 2. Same for this pair, so this I could just compute and not make it the part of the input. And the same for the value of grand coalition. For the grand coalition, we would have to consider all possible partitions, right? So the one partition is singletons. That would give me the sum of 1 plus 1 plus 1, 3. Then there is the pair of 1 and 2 and 3 alone. 3 plus 1, 4, and the other partitions would give me the value of 3 again, because 2 and 3 together get 2 plus 1, and 1 and 3 together get 2 plus 1. So the best partition is 1, 2, and 3, and this gives me the value of 4. Okay, so then we can compute that. So we only specify those values that have some extra value to the sum of the sum of values of the partition, of the best partition of that coalition. Now, this representation still may require exponential space, of course, depending on how many synergies we have. But once again, the hope is that in many practical domains, these synergies are sparse. Now, in terms of complexity of solving different problems, it stays actually NP hard. To determine the values of coalitions in worst case. And in particular, of the grand coalition. However, if this is given explicitly as part of the representation, then it becomes polynomial time to check whether the core of the game is empty or not, which is wanting that. So if we know the value of the right coalition under this synergy representation, then it is poly time to check the non-emptiness of the core. And that's already been done. I'm not for that. So that you know that sometimes there are positive implications of that. Let us look at one more representation, and this one is already multi-issue, and actually you probably will tell me why. This is already sort of fully expressive, and it's called the multi-issue representation. the idea of representing the game is to look at the domains where actually the agents form coalitions to complete particular tasks, to do something together. And those coalitions may require different competencies, different skills, expertise, and so on. And in these scenarios, it may be possible to decompose the characteristic function of the game into characteristic functions defined based on those tasks. So specifically, we would say that the vector v1 vt is a decomposition of the characteristic function v if for any subset of agents C, we would have that the value of C is the sum of these partial values of C for each task. Now I'm saying that this is this representation is fully expressive. Can you tell me why? Any game can be represented this way. Well, the way I decompose V, if I can do that, is up to me. Right? So I can choose the decomposition and in particular into how many elements I'm going to decompose it on my own given the game. The more I find, the better, but it can be just one and then it's just the original game. Okay, so in Rust we can represent actually any game by doing nothing with it. So the original representation can be seen as this presentation with just this is fully expressive representation. We can take just one task. So any game can be given in this form. And now there are some very easy observations about this. If each one of those elements of the decomposition are monotone, all I are monotone, then so easy. That's easy to see. Okay, so if we have some coalition C and we have some coalition C prime that contains it, say the value of C would be this, then now by monotonicity of each one of these guys, this is less or equal than the sum of those for C prime, and that's the definition of the value of C prime, so it is to false. Also, if all those guys are super additive, then so is 3. And that's also just straightforward to see. So if you have two coefficients C and C prime, then the value of their union would be, just by definition, I look at all the issues from 1 to t and take the values I of their union, and now I use the separativity of these functions, and that gives me that the sum of this is, greater or equal than the value I of C plus the value I of C prime. And by linearity we get that that is the sum of those for C plus the sum of those for C prime, and that defines V of C, and this defines V of C prime, so we've got so the game is fully expressive, but it also means that it may take indeed exponential space for the input, but we can hope for good scenarios, because indeed in many situations not all the agents are actually relevant for the completion of each particular task. So for each issue, right, for each task issue we can associate it with a set of agents that actually contribute their skills for completion of that task. And if for each issue the sizes of those sets that this particular issue concerns with are small, then it will become easy to find some solution. So let me just define what I mean by concerning with the set of agents. So we say that the function vi, which is the characteristic function for the issue I, concerns only a subset of agents Ci if we have that the value of some condition S1 would be the same as the value of some other condition S2 whenever the intersection of that collision with Ci is the same as the intersection of the other collision with Ci. And in this case, we would only need to define the function vi over the power set of the set it concern, the subset of agents it concerns with. Because for the rest of them, it will be computable. Right? So instead of, we now would have to define the whole game. We'll take the sum for all those issues. So we would have to define this many values for all the issues, at most 2 in the power of Ci, and that's instead of 2 in the power of n, right? The whole thing. Now, if these sizes are small, then this number may become exponentially smaller than And the advantages that we get from there, that in those situations, where these are small numbers, let's say that the maximum of the sizes of these coalitions is bounded with some constant. Then here we have a constant bound. So that becomes way better than this. And in this case we see we get easy computation of the Shapley value. So this allows the fast computation of the Shapley value. However, checking for the core membership remains hard. So there are some pluses, but not in everything. And it would always depend which representation to choose on what particular scenario you have to deal with. There is one more general representation scheme that we will talk about on Thursday. It is based on the actually logical description of which coalition of agents may or may not form and how much then they can gain together. And I see you then